Look at the sheer volume of global trade moving on any given morning. Millions of tons of cargo navigate across oceans, borders, and continents in a constant state of synchronized motion. Managing this scale of operation requires moving from a linear perspective to a complex systems perspective. A common misunderstanding in business is viewing a supply chain as a directory of static geographical locations, a list of addresses for suppliers and warehouses. This view assumes operations move in a simple sequential chain, progressing point to point from origin to destination. The reality is a multi-directional web of interconnected points, all interacting simultaneously. This structure is formally defined as a network, a structured set of interconnected nodes joined together by active links. These distinct entities tether together to achieve an aligned objective among all participants. The overarching purpose of this architecture is to enable the efficient flow of physical goods, of critical data, and liquid cash. Network design aims for end-to-end value creation, recognizing that optimizing a single firm in isolation no longer maintains a competitive advantage. We can categorize these interactions into 4 primary business networks. These include supply chains for material flows, logistics for physical transport, information networks for data sharing, and partner networks for strategic collaboration. To understand the architecture of a supply chain network, we begin with its nodes. Nodes are the physical or digital entities within the system, such as manufacturing plants, distribution warehouses, or supplier software systems. Since isolated entities produce no value on their own, we introduce links to bind the system together. Links represent actionable pathways, taking the form of transport lanes, data interfaces, or binding legal contracts. The physical structure remains dormant without movement. The network functions only when we introduce flows. The physical flow consists of raw materials and finished products, moving continuously downstream toward the end customer. Simultaneously, the informational flow, comprising forecasts, orders, and inventory data, moves upstream. Finally, the financial flow of payments and credits also moves upstream to sustain the preceding nodes. Keeping this motion aligned requires governance, which establishes the decision rights, policies, and KPIs that define the boundaries of the system. Network architecture functions as a governed conduit designed specifically to balance these trimodal exchanges. Establishing the anatomy of the network is only the first step. The true complexity emerges when we observe how this structure behaves in real time. The defining characteristic of any active network is interdependency. A local change, like a delay at one specific factory, ripples out to affect the entire structure. These structures are also highly dynamic. The network must constantly shift its physical layout and flow rates to adapt to fluctuating demand, changing strategy, and emergent risks. Managing this volatility requires an operational philosophy known as systems thinking. Systems thinking centers on the trade-off between resource efficiency and flow efficiency. When management focuses strictly on resource efficiency, pushing a single node to run at maximum capacity to minimize unit costs, it creates a system imbalance. Local optimization often destroys global value by creating bottlenecks that starve downstream operations. Flow efficiency prioritizes smooth, continuous movement across the whole system, even if it requires individual nodes to run below their maximum capacity. Maintaining this flow requires robust information sharing between every participant. Total visibility reduces uncertainty, preventing minor demand shifts from amplifying into massive inventory disruptions, a phenomenon known as the bullwhip effect. Optimizing a local node in a vacuum often breaks the global system. Systems thinking provides the framework to manage these interdependencies safely. But these theoretical models face immediate, brutal tests the exact moment they are subjected to severe, real-world physical disruptions. Executives use their understanding of network density to design global footprint strategies. The mathematical realities of the network dictate where to place distribution centers and which transport modes will bridge the distances between them. Consolidation exposes the danger of node criticality. Routing too much flow through a single location creates an inherent fragility. Architecturally, this central hub becomes a single point of failure. When a major disruption strikes this specific point, the failure is immediate. The resulting cascading failure halts flows across the surviving grid because necessary inputs cannot bypass the blockage. To address these vulnerabilities, industries are moving toward regionalized networks built with intentional redundancy. Firms increasingly rely on digital networks and AI-driven control towers to provide the real-time visibility needed to anticipate these failures. Modern supply chain management requires building resilience through redundancy, alongside engineering for cost efficiency. Translating systems theory into practice requires a continuous evaluation of the network. The first diagnostic question is, have we accurately mapped all nodes, links, and flows? Without total visibility into the concurrent physical, informational, and financial flows, management operates blind. The second question, where are the bottlenecks or single points of failure? Organizations must audit node criticality before an external disruption forces a shutdown. The third question, are we optimizing local efficiency or end-to-end performance? Pursuing local resource efficiency is an operational trap. The true objective must always be system-wide flow efficiency. True supply chain mastery requires seeing and managing the entire interconnected web, rejecting the illusion of the linear chain.